Okay, so from these axioms, the two axioms, sorry, these 16 axioms from the 10 axioms around the field, and the 16 axioms, sorry, the 6 additional axioms that make a field an order field. With these 16 properties, we can actually prove a lot of kind of operation rules that are actually the rules that you use for dealing with real numbers. So you will recognize them from every math course that you have taken before. So this is again a proposition. So this is the and the numbers that come from the sections of the chapters. Okay, so this is the second proposition in this section of the first chapter. So the following properties hold in any order field. Okay, and this is what sets up the assumption. So if you say hold in any order field, that means you can use all these 16 properties that we have seen before. Okay, so the first one is what we call the unique neutrals. Okay, and so if a plus x equals a for all a, then that means that means that x is a zero, right? This is the property that we've seen before. Okay, this is a number that when you sum it to another number, you get the original number. Well, then x is 0. Okay, it's the same 0 as before. Okay, there are no two zeros for the real numbers. Okay, so if a times x is equal to a, then this x is equal to 1. Okay, so and again, it's important to prove this. Okay, it's not really immediate that these things should be true. But in general, so if you add any number to another and then this number doesn't change, that number has to be 0, and then if you multiply any number by another number x and the original number doesn't change, then that x has to be 1. Okay, so you can make that known, okay, and use this from now on. Now the second one is that the inverses are unique too. So if a plus x equals to 0, then x is the inverse of a minus a. Okay, there's no other number that has this property. And if a times x equals 1, then x is the inverse of a, so a to the minus 1 or 1 over a if you want. Okay, there's no other number that has this property. Okay, so again, maybe this seems obvious to you because are the things that you have been using forever, but the important thing to remember is that these things are properties that you can derive using the axioms before, and they depend completely on those axioms. So if you don't have those axioms, you couldn't reach these properties. Okay, so that's very important. That's why I'm spending a lot of time on this, so that you know where all of this comes from. Now 3, that there are no divisors of 0, so if x times y equals 0, then x has to be 0, or y has to be 0, or both of them have to be 0. Okay, there's no way, there's no number that divides 0. Okay. Now 4, cancellation laws for addition. Well, you have a plus x equals b plus x, then a equals b. Okay. And if a plus x is smaller or equal than b plus x, then a is smaller than or equal than b. Okay, we had seen this before. So you can cancel these numbers, and then cancellation law for multiplication. If a times x is equal to b times x, and x is different than 0, this is very important. Okay, then a is equal to b. Okay, if a times x is greater or equal than b times x, then a is greater than b if x is greater than 0 and the sign of the inequality changes. Sorry, the direction of the inequality changes if x is smaller than 0. Okay, so this is very important, please, because everybody makes mistakes on this. Okay, everybody. If this is true, a times x is equal to b times x, and x is 0, then you cannot make any assumption about a and b. Okay, and actually So don't do that. Okay, so if then you have anything multiplying by 0, you have to be very careful with that. But if x is different than 0, then you can cancel it out. And when you have inequalities, when you cancel them out, you have to be careful about the sign of the number that you're canceling out. If the number is negative, then the direction of the inequality will change. Okay, and that's super important. And you know, people always fail in exams because of these things. So please, please, please be very careful about this. Okay, 6. 0 times x is 0. It doesn't matter which x you write. Okay, minus x. So the inverse of minus x is x for all x. Minus x, you can write it as minus 1 times x for all x. So if you multiply x by minus 1, you get minus x. And then if x is not 0, then the inverse of x, 1 over x, is not 0. And the inverse of the inverse is x. Okay, so 1 over x is x. Okay. Now 10, if x is different than 0 and y is different than 0, then x times y is not 0. And the inverse is the product of x to the minus 1 times y to the minus 1. Okay? And well, this is important, for instance, when you have matrices. So you will deal with this in linear algebra. When you have matrices, this thing is not true. Okay? And that's because the multiplication for matrices is not commutative. Okay? Because A times B is not B times A in general. Okay? And so the inverse of these products are not the same. Okay? So just remember that. But with real numbers, this is true. Okay, so if x is smaller or equal than y and 0 is smaller or equal than z, so z is a positive number or 0, then x times z is smaller or equal than y times z. Okay? And then if x is smaller or equal than y and z is smaller or equal than 0, then x times z is greater or equal than y times z. Okay, so again, if the number that you're multiplying an inequality with is negative, then the direction of the inequality will change. And then if x is negative, smaller or equal than 0, and y is smaller equal than 0, then, sorry, this got cut up. X smaller or equal than 0 and y is smaller or equal than 0, then the product will be positive, okay, or 0. And then if x is smaller or equal than 0 and y is greater or equal than 0, then x times y is smaller or equal than 0. Okay? So that's it. This is just what you know. If you multiply two negative numbers, you have a positive number, and if you multiply a positive by a negative, you will have a negative number. Okay? Now, 0 is smaller than 1. You can prove it using the axioms directly. And then x squared, so the square of x, so that means x times x. Okay? X times x is greater than 0 for all x. Okay? And well, it's easy to prove this from this. Okay? So if x is positive, then you have positive times positive. We know it's positive. And then if x is negative, it's negative times negative, which is positive again. Okay? And if x is 0, the only way that this is 0 is that x is 0. Okay? So, for instance, we can, and now we can start, you know, trying to do things with real numbers. Okay, so for instance, we can prove it. Think about, you know, prove this thing. So how do we know this is true? Okay. Because it doesn't seem obvious. Okay, we are going to use this property 14. Okay, so we start from this statement: a minus b squared is greater or equal than 0. We know that, right? Now we use the distributive law to expand this. We know that this is this. Okay, greater than 0. And then we subtract well, we sum 2 times AB in both sides. Okay, and then we divide by 2, or we multiply 1 over 2, and because 2 is a positive number, then the sign of the direction of the inequality doesn't change, and we get here. Okay, so you see how we can prove things like that. Okay, and then for instance we can, so yeah, if you don't know this, these are things that you need to know. A minus b squared, you prove this using this distributive law. So this is just a squared minus ab minus b times a minus b squared, but ab and ba is the same thing because the product is commutative, so this is just minus 2 times ab. And this, if in the case a plus b squared, this is a squared plus 2ab plus b squared. Okay, and finally a plus b times a minus b, so the multiplication of the converse is just a squared plus minus ab plus ba minus b squared. So this is a squared minus b squared. Okay. So these 3 identities are very important, and we will use them throughout the course. So just in case you didn't know them already, they're here for you. So yeah, that's it for now.